the first one. Okay, sorry. Yeah. So that's now the first realization. So, sorry. Jusak. We talk about the Leptoquark effect in the real Hyperon and the Kaon processes.
Okay, thank you. So this is this talk is based on the coding work, which we hope to finish soon this month. So it's about Leptoquark effects in Orion, Hyperon, and Kaon processes. Okay, so this is the outline. So I'll give a brief introduction to hadron decays with missing energy, strange hadron decays. Then I'll try to show that Kaon and Hyperon decays are actually complemented probes of new D-quark, S-quark interactions with invisible fermions. And then I'll discuss specifically about how leptoquarks, more specific model-specific scenario where you have leptoquarks contributing to these processes. So and here I just discussed the same model independently, but here I have a leptoquark model contributing to this process. And then I'll finish. Okay, so the process I'm talking about are these flavor changing neutral currents, which also involve missing energy. As probably you know, flavor changing neutral currents in the standard model are induced by a loop diagram, like this, for example, especially the process I'm interested in of this type. So you have SD quarks, and then you have missing energy. In the standard model, it's carried away by para neutrinos. And so you have these loop diagrams. So because of these loop diagrams, you have loop suppressions and also you have J mechanism. And so all of these factors contribute to result in very small branching fractions. So for this type of decays in the standard model, you have branching fractions of less than 10 to the minus 10, especially for the well-known famous Kaon processes, K2 pi nu here. For these modes, you have these predictions in the standard model. So they are less than 10 to the minus 10. Okay, so that means if you look for these processes, this type of processes, if you see something which are significantly larger than these numbers, then that's probably needed.
Let me ask you a question. 30 years ago, there's a charge K to charge pi mu bar used to be like 10 to the minus 10. But why now it's like a few factors smaller? Now it's almost 10 to the minus 11. During the past 10 years, what's going on?
This standard model prediction.
I know, but standard model prediction 20 years, 30 years ago was larger.
Well, maybe the CKM factor.
Better? Smaller? Okay.
Well, more precise.
How far is the same?
Well, yeah, I don't know. Yeah. But I think the CKM we know better, and Leptoquark mass we know better, and the charm contribution also. But this Buras in this group.
But that one's always 10 minus 11.
Yes.
The charge one seems larger.
Yeah, I'm not familiar with the old result.
I want to familiar with the old one.
Okay, now the data, especially for this K25 missing energy. So these are the current data. So that's what I showed before. So up to before this, up to this summer, this past summer. So we have these results. So these are already close to the predictions here. And similarly also, well, this is a little bit bigger than the prediction. But they are very close to each other, basically. And then...
Which experiment for the charge pi? Charge again? Which experiment?
I think it's E949. I think probably that's the last one. The latest.
NA62 recent.
Oh, the most recent, yeah. This is older. I'm talking about. I think, yeah.
The old one, there's one data. Basically, now it's not right. Yeah.
This
Okay.
one,
You should not trust this one.
Well, that's the official up to now still. Okay, now this is what we have this September. So NTHU has new results, new limits, but these are all preliminary. Okay, so they have not written any public papers yet. And so now you see these upper limits here. These are twice the standard model prediction, central value. But when you look in terms of plus minus is given by this number here. But essentially, this is very close to the standard model. But this is still consistent with the old result, the PDG result.
No, just one few words. The last one was done by Tran and Brohaden. They found out 2.5 event, but later on, the internal node, they said that one of the event is wrong. So that's why the current one, they push to the NTHU. I think this is yeah, okay. Yeah.
Okay. Now, this is the intriguing thing from Koto. So Koto, they announced that again, it's a preliminary results. They saw 3 events. Okay, 4, but they say 4, but one of them we already think was background. Yeah. So if you multiply this by 3, you get a number which is about almost 2 orders of magnitude larger than standard model prediction. So right now they are still doing more checking and whether these numbers are correct or not. And so at the moment, these events appear to be anomalous. So we call it Koto anomaly. So we are waiting for some new result, but these events may go away or maybe they are real. But whatever the result will be, it's important that we explore these kinds of processes, and so that means it's not enough just to study K2 pi missing energy or K2 pi mu, because it turns out that if you look at the possible underlying operators, there are other possibilities, other operators that are not probed by these decays. Okay, so that means you need other processes. So that means not enough that you only study this K2 pi missing energy, but it's important also to study K2 pi missing energy or K2 missing energy. Actually, these 2 probe operators are different generally from the operators probed by K2 pi missing energy. Okay, so that means these measurements hopefully will also be done, especially these ones here. I think in the charge mode case, NTHU can do it, and Koto can do the neutral mode also. And so in the near future, we may get updates on these results. But at the moment, these are the current data bounds. Now, as I mentioned, the data here indicate that maybe if there's new physics here, the new physics is not very large, okay? Because they are already very close to the standard model prediction. Aside from the possible Koto anomaly, of course. If the Koto anomaly is there, then of course we are all excited because that's new physics. But if it goes away, then the possible new physics will again be small. But that, if you look at the data for the other ones here, it turns out that the current data are still much larger than standard model prediction. For example, these ones, the standard model, they are predicted to be 10 to minus 13 orders. Okay? And similarly here for this one, these are also much larger than standard model prediction. And so that means new physics may not enter this very much, but they may still enter these other processes. Okay? And as I mentioned, other operators are still possible which are not yet probed by K2 pi missing energy. Now, what about the baryon sector? Now, it turns out that in the baryon sector, things are actually good if you have the data. At the moment, we still have no data. Because in the baryon sector, it turns out that especially for the spin-half Hyperon decays, the spin-half Hyperon can probe all of these operators that are probed by the different Kaon modes. And so that means if you can measure the Hyperon spin half Hyperon decays, and also the spin 3 half omega minus Hyperon, then you can actually get complementary results or information about the possible physics of the underlying operators. Okay? And hopefully BESS3 can do that in the near future, and BESS3 is actually starting to look into Hyperon decays into another baryon and missing energy. Okay? And hopefully they will get new results in the near future, very near future. Okay, now if you're not familiar with what a Hyperon is a baryon containing at least one strange quark. Okay? So for the spin half case, these are the Hyperons. For the spin 3 half case, these are the Hyperons. And the ones that I'm interested in here are the ones that decay weakly, okay, mostly. So these processes here, and also omega. The other ones here actually turn out to decay mostly to strongly or electromagnetically. So these are the Hyperons. So I'm looking at processes with these. Okay, so now, as I mentioned, there are operators that contribute differently to these different modes. Okay, so if you look at more generally, you can write down a bunch of operators like this. So you have S and D quarks, and then you have the unknown fermions. Well, this F could also be setup model neutrinos, but this could also be invisible fermions other than in the standard model. Okay. And so, in general, these contribute differently to the different modes here, Kaon modes or Hyperon modes. Okay. And the reason is this quark bilinears here in these operators. So the ones with gamma 5 contribute to processes with only one meson or 3 meson. Okay. So the ones with gamma 5 contributes to K to missing energy and to K to pi missing energy. Okay. But the ones without gamma 5 contributes to K to pi missing energy. Okay. But for the spin half case, actually, all of these contribute to this spin half Hyperon process. And for the omega, this all gets mostly from the ones with gamma 5. Okay. So you can make a summary like this. Okay. Well, let me mention that the reason for why the different operators contribute differently, and that's the reason is that the hadronic matrix elements of these operators, so the matrix elements of these quark bilinears here, some of them are 0 or not 0, depending on the processes you have. And that's the reason why the different operators contribute differently to some of the different modes. So in summary, you can make a table like this. So for these operators, which I already wrote down, so the ones what's in purple here have no gamma 5 in the quark bilinears, and so this contributes to the K to pi missing energy, but also to the spin half Hyperon modes. But the other ones with gamma 5 contribute to the other ones. Okay. So again, this spin half Hyperon modes can cover all of them. Okay. Now I just want to mention very quickly. I have only 5 minutes. So in the standard model, as I mentioned before, the predictions are very small for these types of processes. So 10 to the minus 13 in this case for the Hyperon, even smaller than the Kaon case, K to pi missing energy. And these are, now BESS3, as I mentioned, is looking for these Hyperon processes. It turns out that the BESS3 sensitivity is basically given by these numbers here, and these numbers are much higher than the setup model predictions. That means it's hopeless for BESS3 to look for a setup model. But then, as I mentioned, it's possible for new physics to contribute to the underlying operators. Okay. And so you can do actually a model independent analysis, and that's what we did, and you can get some actually enhanced branching fractions from operators which are not constrained by the current K to pi nu data. Okay? And that is, this is the result. So for those operators that are not constrained by K to pi nu, the main constraint actually comes only from this processing, which actually has very weak constraint at the moment. Now, with that constraint, actually I get these upper limits on the branching fractions of the Hyperon modes. And actually these numbers, the upper limits here are larger than the sensitivity reached, sensitivity limits of best 3. In other words, these numbers are within the best 3, the proposed best 3 sensitivity reach. Okay. And so now, what I did here was just a model independent study. Actually, you can do similar study with other processes like scalars, for example. It turns out situations are similar, invisible scalars. Okay, and well, in this case, actually, I'm not showing it here, but actually, in the numbers I showed in the previous slide, I assume those new particles or the fermions are massless. But if you make them not massive, massless, it turns out that the constraints are weaker from the Kaon case, and so you get even higher branching fractions for the Hyperons. Okay, so now I have those predictions from in model independent study. So the question now is, can you find a model, specific model where you can achieve those high numbers for the upper limits for the Hyperon branching fractions? Now, it turns out that I think you can find those branching fraction, high branching fraction predictions in some models. And in this case, we study the Leptoquark model. Okay? Now, we choose only scalar Leptoquarks. In general, the scalar Leptoquarks that have been much studied in the literature are these 3 here. And so you could have these couplings to standard model fermions of these Leptoquarks. And so these are all, again, well known in the literature. So I just use them from the literature. And from here, you can have this kind of diagrams where you could have standard model neutrinos here interacting with the SD quarks mediated by a heavy Leptoquark. Okay? And so you get this, it turns out that not all of the operators I wrote down get contributions from here, only these 4. And so from here, then you can write down the formulas for the coefficients. Now, actually, in this scenario, I'm also assuming that you could also have right-handed neutrinos, right-handed neutrinos. And in this case, you also have these couplings here. And so if F here is a right-handed neutrino, then you also have these coefficients. And then, again, as I mentioned before, these will contribute to the different processes. Okay? And so basically you can kind of repeat the analysis you did before and get some results. But then, of course, these Leptoquark interactions also contribute to other processes. And that means we need to consider constraints from those other processes. So this is what's one of the differences between this model-specific analysis and model-independent analysis. The model-specific analysis, you have more constraints in general for the couplings you have. And so one of the main constraints is from Kaon mixing, because you have S and D coupled to these Leptoquarks and neutrinos. Yeah? And that means Kaon mixing will get contribution from these numbers. Now it turns out that you could actually, if you choose the matrix elements of the Yukawa couplings here judiciously, you can actually completely evade these constraints. Okay? Another constraint is from lepton flavor violating SD interaction. Okay? Now this was similar to SD missing energy, as you knew. This is induced at tree level by the Leptoquark. Okay? So you have these interactions. Now, as probably you know, in here, the constraints come from the E mu or flavor changing contribution. For example, K to E mu or K to phi E mu. These have very stringent experimental limits. Now again, you can also evade these constraints by judiciously choosing the elements of the Yukawa, of the Leptoquarks. Okay? And this is also even mu to E gamma and mu to 3E and mu to E transition constraints can be evaded. Okay. Now, it turns out that the constraints that we cannot avoid, okay, are the constraints from tau decay, lepton flavor violating tau decay. It turns out that in this case, if I have this, okay, so in this scenario, I assume that we do not have contribution of right-handed neutrinos. This kind of phenomenon. So these constraints then allow me only to get these numbers here. Now these numbers actually are lower than the S3 sensitivity reach, but they are not much lower. So maybe in the near future when we have super Chantal factories built, maybe in China or Russia, then they may be able to reach these numbers. But actually something, you can still get a better situation by, instead of the Leptoquark couple to set up model leptons only, in this case I'm assuming Leptoquark couple also to right-handed neutrinos. It turns out things are actually better here because now you can avoid some of the constraints that you get if you only have coupling to charge leptons. I mean, set up model leptons. Okay, so if you have right-handed neutrinos coupled to the Leptoquark, you can get couplings that can evade many of the constraints I had before. So in this case, I can get a larger result, similar to my model independent study. Okay, okay, so I'll leave the conclusion page. Thank you.
Any urgent question? Okay, no, okay, so.
So you have Leptoquark, so do you have any implication for D to tau nu process?
D to tau nu.
Because you have Leptoquark, so you can connect quark and lepton.
Yes, the principle you could get a contribution.
Once you assume that some specific flavor structure on that coupling, you can simply avoid or contribute. But I just wonder if you can have
D to tau nu, maybe there's some contribution there, but I don't think it's strong constraint. Why? Are you interested in that?
Yeah, because you just have Leptoquarks.
Okay, well, yeah, it can contribute to many processes, but that process D to tau nu I'm not familiar with, but maybe the data are not very precise, so it will not probably constrain the coupling very much.
Thanks, you, Jusak.